OK, so I need a little aside here in order to proceed with what I want to talk about next. And that is, I just want to define for you how you would define lambda QCD at higher orders in perturbation theory. So the formula we had used a minute ago is leading log. But we can define lambda QCD even if we go to higher orders. And I just want to do a little bit of algebra, set up some notation in order to define this thing at higher orders. So ms bar beta function and we're going to just work to all orders formally. And we'll see that we can construct a solution where it's kind of obvious how you would work to whatever order you want to work. So let's just parameterize the series, even if we don't know all the terms. We only know up to beta 4. But let's just parameterize the series as a bunch of betas. I'm going to call the cutoff R because we've started calling it that, but I could call it mu. I just took mu equal to R. So I can rearrange that equation in this way. I can write it as dr over r is equal to d alpha over beta. And then I can integrate on both sides between two values. And on this integral, it's just giving me a log. This integral is giving me an integral over alpha. So what I'm going to want to do here is make a change of variables. And we'll see that the following change of variables is convenient. I'm going to make a change of variables in the integration to this t. So I have some dummy variable that I'm integrating over. Let's change the dummy variable t. And basically, that's going to simplify the lowest order result. Because the lowest order result, d alpha over beta of alpha, well, the beta goes like alpha squared at lowest order. So I'm basically making a change of variable where this d alpha over beta at lowest order will just be dt. That's what I'm doing. I have to change variables in the limits as well. So call those t1 and t0. And change variables consistently everywhere. And if I do that, this is the kind of form of the result. So this is just a Laurent series in 1 over t. And the first term we had d alpha over minus beta naught over 2 pi alpha squared. And that was just minus dt. And so the reason that this thing here is a 1 is because my change of variable with dt was exactly taking into account all the factors to basically just make it into a 1. And there's a sign change, but I flipped the limits. OK, so we made the first term trivial, and then the higher terms are these terms. And these b hats, we could figure out what they are. And they're just combinations of the beta functions. So once we expand the 1 over beta, we get various combinations of things. I think I won't write V3, but we could also do the integral. Pretty easy integral to do. And so if you want to write a solution for what the integral is, you could say it's, well, it's some function that you get from doing the indefinite integral, evaluated at the upper limit, minus that function evaluated at the lower limit. And g is just that function. So doing the integral of 1 gives t. Doing the integral of the other term and being careful about what's positive and what's negative, I can write as log of minus t. So t was negative. If you look at my definition of t, it had a minus sign in it. So this log is a log of a positive number. Okay, so we have this g of t, and g prime of t is just b hat. And if we write a formula, which is not what we're actually interested in here, but might as well write it anyway, if we write a formula that's this way, just taking that formula and writing it this way, then if you think about what this formula is, it's an all orders relation between the coupling at one scale and the coupling at another. It's a formal relation because you need to know the coefficients. But if someone tells you the coefficients, you can just plug them into this formula. And this is the extension of the usual running formula that you would write down for relating alpha at one scale to alpha at another scale. This is a generalization that includes higher order terms in the beta function. So the other thing that we can do is we can rearrange the formula and take account of the fact that we have R1s and R0s, and we can make it such that we have only R1s on one side of the formula and R0s on the other side of the formula by splitting the log into two pieces. And that's what you do to define lambda QCD. So we can rearrange it as follows. Take in an exponent. So now we only have R0s in this part, R1s in that part. This thing has to be independent of the choice of the R, and that's just this constant, this lambda QCD. And that's the generalization of this definition of lambda QCD that we had before, where it was R0 e to the minus 2 pi over beta naught alpha. Now we have the higher terms. They're just encoded in this g function. So if you didn't remember that formula for the lambda QCD, now we've derived it. And we've included the higher order terms as well, so the next term would be this, and then there'd be higher order terms, and usually you call this the leading log expression for lambda QCD, and this the next to leading log once you include that term, et cetera. Okay, but the whole combination is mu independent. The mu independence of this term is only canceling to leading log. Once you include this term, it's canceling to next leading log. The whole thing is mu independent, giving this lambda QCD. Okay, so that's end of the aside.